Hi, and welcome back to Econometrics B. So today we're going to continue talking about corner solution outcome models and censored regression models. So we've already talked about TOPIT and how that can be used to, consider these two cases, both corner solution outcome models and censored regression models, both resulting in mass points at certain parts of the distribution of the variable of interest. So today we're going to look at specification issues in estimation under weaker assumptions than those we made for the Topin model. So I'm going to start with a little bit of a recap on the estimation of the Topin model, and then I move on to talk about neglected heterogeneity, heteroscedasticity, and non-nullity, and then to estimation under weaker assumption. And we're going to talk about something called the CLAD estimator, or the centered least absolute deviation estimator, by James Powell, also sometimes called the Powell estimator, and how to make inference and get standard errors for that, and how to maximize or minimize the objective function. Turns out to be some computational issues, and it turns out that we cannot just use the usual theorems for inference from the theorems about M estimators directly. So we can use bootstrapping to get the standard errors. Bootstrapping is kind of a simulation way of estimating the standard errors by resampling again and again from your data set. You think that may not be possible, but it works surprisingly well. So I'm going to talk about that at the end. Okay, so here we are with the TOPIT. So we have our two quantities of interest. This is just a recap. In data censoring case, we would be interested in the latent variable y star, conditional on x, or simply just the parameters beta in this model down here. Okay, so here this would be our y star. So we would have a model for that latent variable that is just a linear index plus some error. Okay, in the TOPIT model, we assume that error is normally distributed with a constant variable, or constant variance that does not depend on x. Okay, so the fact that the distribution of u conditional on x does not depend on x, well, that implies homoscedasticity. Okay, so we can use this model to estimate basically beta, and we can then basically we can get our object of interest, which would be the conditional mean of y star given x, or x beta. Or we could just simply get beta, which is the partial effects of those. Our leading example here was the top coding of wealth, or censoring of some variable due to a recording issue. So that's one case. And then the other case, that is the corner solution outcome case, where we would be interested in whether the observed variable y, which would be what you have here, the max of 0 and x beta plus u, whether that is, what is the probability that that is equal to 0, or that it's non-centered, or that we're not in the corner solution, or what is the overall conditional mean of y given x and y given x, and that conditional on y being positive. I think we should just have a comma here, right? But you know what I mean. Okay, so with this model, under these assumptions, we can estimate this model with maximum likelihood, and the log likelihood contribution for observation number I has this particular functional form. We spent some time on deriving this last time, so I'm not going to spend more time with this. So if you want to estimate the TOPIT model, you can just do this in a standard conditional maximum likelihood framework. You maximize the sample average of the log likelihood contributions, or if you will, minimize the negative of them. So that's that's supposed to be known. So now we want to move on here to talk about neglected heterogeneity. Okay, so what happens if we're not, our specification of the model was not completely accurate. We had the model completely like before, but now we have this additional term, gamma c, which is unobserved to the contrition. Okay, so there'll be an unobserved component or random variable here that we cannot observe, and that's why it's going to be in the error term. Now, depending on the nature of this error term, or this additional neglected heterogeneity, we can do different things. Okay, so we recall basically from the binary response models that neglecting heterogeneity, well, that had an effect on the estimation of, or the size of the parameter estimates, because they were scaled relative to the residual variance. So we want to analyze what is going on here. Now, okay, we're still assuming that U conditional on X is independent of X and has zero mean. So, but now we also condition on C, okay? So we can assume that C is a little bit like a random effect. You know, it's not correlated with the explanatory variables, okay? Now, if we were to do, if we were to observe C, well, we'll just include that as an additional regressor and do, you know, ordinary Topit analysis, and everything would be fine. And so, you know, then the question is, what can we do now? Well, we can derive the density for Y conditional on X and C, but then as usual, you know, we can only condition on things we want to observe, because if we want to, like, say, maximize the likelihood function, we need to be able to compute that that conditional likelihood, and we cannot condition on things we do not observe. So, you know, how would you calculate this formula here and add it to your likelihood contribution if you don't really observe what C is? So we have our usual, not trick, but, you know, the usual, again, that would be either try to make some transformation to get rid of C, or say assume some distribution of C to integrate that unobservable out. And we're gonna, you know, try to do the latter here. So let's assume that it has a distribution H conditional on C, and then what we'll do is we can express the density conditional on X only by integrating that out. That is taking the expectation with respect to C conditional on X, the stuff we already choose to condition on, and we can do that since we now have a distribution for that condition for C conditional on X. So this is what we get, and then depending on whether this C here is a discrete variable or continuous variable, well, then you're going to have that expectation being expressed in either of these two ways. So, you know, if it's a continuous variable, well, then you multiply with the density and integrate over the support of C, and then you get essentially your conditioned out that unobserved C. Or if you have a discrete variable, well, then you sum over all the different values of C and then multiply it with the probabilities that these are occurring. So it's like a, you know, probability weighted average of the conditional densities where you've conditioned on C. You know, very intuitive. Okay, so we're going to look at these two examples one by one and see what are the implications. So first, we're going to look at the heterogeneity example with a discrete case. Okay, so here I have like two latent types in the population. You can have more types if you want it. Okay, so so here we're going to assume that the distribution is the following: this discrete distribution with probability pi when C is equal to a h. So that is, you know, we're a high type. Okay, so C, our unobserved heterogeneity, it takes a high value. Or with probability 1 minus pi, well, then you have that low type. You know, this is completely analogous to what we did with discrete choice models for pan data, where we're also looking at these two different types. Okay, so and again, here we just get additional parameters to estimate. So we would estimate pi, and then we would estimate HL and H high. Okay, so actually it's not entirely accurate. You may want to make an identifying assumption here, so that the mean of these two errors or these two types is in fact equal to 0 or something. Okay, just like we did before. So really, we actually have only two additional parameters in this case. So I leave it at that, and then you can consult our discussion during the discrete choice case, where we also looked at the distribution of types. Okay, you know, alternatively, you could just leave out a constant, and then you could actually estimate these two parameters freely. So here is the so we can see here the basically it changes. It's going to be a more flexible specification, and with this specification, you cannot really, if you think these types are discretes, well, maybe you have to account for that. Okay. Now, let's assume a continuous distribution now, and let's assume the very particular distribution of the normal distribution. So we assume that this unobserved variable c conditional on x is normally distributed with some variance tau squared. Okay, so this implies that c and x are independent. Okay, it's not only implying that they're mean independent, because the mean, well, it does, because the mean is equal to 0. So the conditional mean of c given x is equal to 0. But the variance is also independent. So there's no homoscedasticity here. Or sorry, heteroscedasticity. The variance of c conditional on x does not depend on x because there's no x over here. But not only that, because we have the entire distribution of c conditional on x being described by only these two moments. These are the sufficient statistics for the entire distribution. This means that not only is c mean independent on x and homoscedastic, it's completely independent, because all other moments, the skewness, the kurtosis, and so on and so forth, they are also independent of x. So the entire distribution does not depend on x. Okay, that's why we call them independent. And you can say, actually, in our Topit formulation, let's go back, that's the exact same thing going on here. We are assuming that u conditional on x is completely independent, is completely independent of x. So this is a very strong assumption, okay? So we're assuming more than just mean independence and homoscedasticity. We are assuming complete independence of u and x and c and x. Okay, anyway, so this is, we're back in our heterogeneity case where we make this assumption here. So this is like a pretty strong assumption, but you know, what is going to give you? Now, if you have this assumption, it means that you can essentially write C as C equal to you can essentially you know, substitute here C here, that's a normal distributive variable. This is our model here with the heterogeneity. But then the sum of u and c, since both c and u are normally distributed, well, the sum of them, v, is also going to be normally distributed, but with just another variance. Okay, so we use the variance formula for the sum of two independent normally distributed variables to calculate that variance. Okay, and so that's what you see here is really what you get is another Topit model with just a with just another variance on the error term. Now here I'm talking about it as if it's the cross-sectional case. And of course, if you were having a panel data case and this was individual specific and this would vary over the alternatives, well, then you would have to do something called like the pool Topit, or maybe a random effects Topit. And if you did the latter, then you would take into account how the structure of this joint error term would be, you know, serially correlated over time due to the persistence of this variable. So that's completely analogous to what we would have done under the discrete response model that we have looked at before. Okay. The bottom line here is that you can just proceed and do standard Topit analysis if you think your neglected heterogeneity is still normally distributed. Okay. It's just that the variance estimate is going to be bigger. Okay, now let's talk about some of the key specification issues that arise in the Topit model. Turns out heteroscedasticity and non-normality really have both severe consequences, essentially because we are misspecifying the model. These are not resulting in the linear model without any centering in any inconsistency problems of our estimator. Okay, remember, if you were to do a linear regression model, you don't have to assume anything about the distribution or how the variance or other moments is related to the explanatory variables in order to obtain the OLS estimator. That can be derived solely under the assumption that the conditional mean of the error term given x is equal to 0. So only mean independence. Okay. So, but that's not the case for TOPIT. In TOPIT, you get inconsistent estimates for beta if you have heteroscedasticity or non-normality, or in fact, if any of the other moments higher up are potentially affected by x, well, you have the same thing. So we need to have this underlying distribution. Of course, the degrees of misspecification and the consequences of them, well, that depends on what it is that is misspecified. But generally, you're going to get inconsistent estimates. Why? Because really, the derived density of y given x hangs crucially on the latent variable being normally distributed. Okay, and that the error terms are mean independent of the explanatory variables and normally distributed. So that's why. Okay, and so you can see in censoring is actually really costly, and it's the more censoring you have, the more you're vulnerable to these potential misspecifications. So in absence of censoring, we would consistently estimate beta, just like I said, under that conditional mean assumption. Also, recall from our derivation of the objects of interest under the corner solution outcome model last time, the conditional mean, for example, the probabilities, all these things depends completely on the underlying distribution that we are assuming for u, okay, and now therefore also for y star. Okay, so it had like the inverse Mills ratio, it has the CDF of the standard normal, it has the PDF of the standard normal appearing in all these different equations. So of course these expressions are derived from the underlying assumptions. So if the underlying assumptions are not true, so we don't have the normal distribution, well, you're not going to have those expressions. You're going to have some other expressions. Okay. So the bottom line is it's actually important to test for these misspecifications, and it's more important the more censoring you have, okay, or the more people that will be in the corner solution outcome. Okay, so I'm just going to do a little bit of illustrations here and need a little bit of Python modules here. I've collected all the functions that we need for this notebook here in this Python file called creg that has a bunch of things on censored regression models and corner solution outcomes, including the TOBIT, for example, and some of the estimators that you'll see. Okay, so let's do a small simulation exercise first, okay, just to illustrate the problems of heteroscedasticity and non-normality. So we consider the following model, okay, so it's very much along the line what we had talked about previously. Now I've added a little bit of room here for some neglected heterogeneity. So if you put gamma equal to 0, well, there's no neglected heterogeneity if you do that in your data generating process when you try to estimate back the parameters. Now I also I'm assuming some more general specification for the distribution of U conditional on X and C. It's distributed according to this CDF, we call it F. It has mean 0 everywhere, and then the variance we may allow that to depend on one of the explanatory variables. In our case, it's just going to be the last one, the kth explanatory variable. Maybe I should have like a capital K here, to be specific. It's the last one. And then C here, we can assume is just standard and normally distributed, not to carry around the tau. So that would be like, we would assume tau in the previous slide to be equal to 1. Now let's just return to F here. F can be many different things. For example, we can have F just being the normal distribution. Then you could just have N right here, okay? You can have a log normal distribution. You can have a mixture of true normals, and all these things are implemented in the code. Okay, so you have there's the implementation with a symmetric or an asymmetric distribution. So I do this to see, okay, what happens if I'm trying different distributional assumptions when I then generate the data and then estimate the model with a TOBIT? Would I still get a good estimate of beta? Okay. Then to make things comparable, I do a little bit of I normalize all the variance of this residual error term to be equal to 1 throughout. Okay, so some of these distributions that I'm choosing are involving different variances, but then I just normalize it at the end, so everything is this variance u here is sigma, so that the joint variance of sigma u, well, that would be sigma squared. Okay. Then we have, yeah, and I think I kind of, I've said here. So basically you have U is homoscedastic if delta is equal to 0, and you have no neglected heterogeneity if gamma is equal to 0. Okay. So, and this is all implemented in this function, sim data that that I have ready for you right over here. Okay. So, and then it calls this simulation of errors. Here you can look at the different type of errors. I'm not going to dwell so much into it. I think it's better just to look at the specification here. There's some details buried in the code, you know, about how those mixtures of normals are looking, but I think it's just better just to look at the distributions, and then that'll be clear. Okay, so here's an example. Let's start with the simplest case first. So here I choose n here, that is the number of observations. We start with 5,000 of them. We have beta, that's 0 and 1. And then the first explanatory variable, that's just a constant, and all other explanatory variables, they're just randomly distributed between, uniformly randomly distributed between 0 and 1. So they're all positive. Okay, it's just to make it easier to understand what the coefficients mean. And then we have basically sigma. Okay, that's the one that scales up u, whatever distribution that is. And then we have gamma, the one that controls the amount of unobserved heterogeneity. So essentially this parameter here. And then we have delta, the one that controls how much heteroscedasticity we have for a given distribution. Okay. And then error type, that's essentially choosing F. Okay, so you can choose many different parameters, like a normal, a log normal, a normal, uniform log normal, a mixture of two normals, and then I have two different versions, where one there is like an asymmetric distribution and one where we have a symmetric distribution. Okay. And in either cases, whatever you do, you will see the distribution of the error term down here, and then you'll see the distribution of the observed variable here. Okay, and then there's some estimates. So I encourage you actually to, you know, try and play around and see, okay, what's happening to the Topit estimates and those distributions under different assumptions. And I'm gonna try the first thing. So let's see. This is the basic case where we have basically everything is derived under the assumptions of the Topit model. Okay, so for example, we have normally distributed errors. There's no heteroscedasticity. There's no neglected heterogeneity. We have a variance of the error term of 1. We have two coefficients. Okay, and it looks like these two coefficients, 0 and 1. Well, Topit is really nailing it. It is saying the first one is significant and the other one is pretty close to the true value. You see here's the sigma parameter. Well, that's an additional parameter we talked about last time. That was something we could identify in contrast to the case of binary response, and we can estimate it to be 1. And you can try to play around with some parameters. You see here, this increases the variance of the error term. If we make the standard deviation 2, that it results in a little bit more, in this case, some more truncation, but we can still estimate the parameters. The standard errors are increasing a little bit, but that's kind of expected if you have more variance of the error term. Okay, so that's basically what we have. So and you can play around with the other parameters and see if Topit is doing a good job in estimating it. So then we have, say, let's move on and talk about the neglected heterogeneity. So that is our case here, where the neglected heterogeneity case with the normally distributed unobserved heterogeneity. Okay, and we learned that we should basically get consistent estimates of beta, but then we would just get a little bit higher variance. Remember, tau now is 1, so it's really basically the variance we estimate here is gamma. It's gamma squared plus sigma squared. Okay, so let's see if we get that. and let's just put them equal to 1, both of them. Then it's easy to square them and take the square root of 2 is supposed to be like, something like 1.41. So let's see how, if we can get that. Well, we still get the same, right? The same standard, or the same, estimate the coefficient on the explanatory variables to be of the right magnitude and sign. And so we have this is supposed to be 1. It's fairly close to 1 measured by the standard error, and this is supposed to be 0, and it's also insignificant. We have the standard error here, or the estimate of the of sigma will, now that measures the joint variance of the unobserved heterogeneity and the error term that we estimated before. So it's no longer just 1. It's supposed to be the square root of 1 plus 1. Okay, so it's like the square root of 2, which is, I think I can't, on top of my head, it's something around 1.42 or something. Okay, maybe we should actually, actually print it out and see if we get that. So I'll just, and so what is that? NP square root of 1, 2. So 1, yeah, 1 plus 1. Well, that is supposed to be, where is it printed out? QRT. And that's what we get, 1.11. So I was not actually completely accurate with my remembering of the square root of 2, but it's 1.41. Okay, and let's see, you can just increase the number here, and you see here it's decently close to that number. Okay, within the standard deviation. So that seems like it fits with the theory. And the bottom line here is you can do standard Topit analysis, and usually you would be interested in just this parameter, and that's still consistently estimated. Okay, so crank down the observations a little bit, and let's move on and just put this to 0. We have analyzed neglected heterogeneity now, and let's see if it can handle some heteroscedasticity. And so delta here, that's the parameter over here that is controlling the dependence of the variance of one of the explanatory variables, in this case x1. Okay, it's the only 2 explanatory variables, x0, which is a constant, and x1, which is just the standard or normally distributed variable. So as we increase delta, you're going to get more and more dependence on x, and you're going to get more and more heteroscedasticity. So that's not going to be so good for our estimator. We can look at it. Well, with delta equal to 1, it's not so bad, but still we get estimates that start to look a little bit hairy, right? These are significantly different from the true value. You add 2 times the standard errors on either side, and then you see really true value is not in the confidence interval. And things get worse if you add more heterogeneity. Or more heteroscedasticity, then you also start to see that the error distribution is really looking funny. It's not looking like a normal distribution anymore if you just look at it and unconditional on u or unconditional on x, but just the distribution of u, the marginal distribution of that, and then also yeah, so we have some issues here. So and the bias gets more funny. And it was before, and we even get like significant negative constants and whatnot. So it looks like this is not good for Topit. Okay, so that's one. Let's look at the last example. Say, okay, so now we have no longer heteroscedasticity, but what if we say it's say, for example, it's a skewed distribution, a log normal. Normal. You can write anything here. that is on this list up here, and yes, well, again, we get something that is definitely not equal to the true value. They're supposed to be 0 and 1, and so that's not good for Topit. We're now misspecifying the distribution of the errors. It's not that there's anything wrong with the log normal. It's just you have to write up the estimator under the assumptions that are true, and we have assumed a different distribution than the log normal, so that's not good, right? And let's see what happens if we say increase this parameter here, the constant. What would that mean? If you look at the distribution down here, you start to see that now suddenly there's no mass point anymore. And all the observations are censored. And this is even a skewed distribution, but yet our estimate of X is actually pretty close to the true one. Okay, this is the kind of performance you get in a linear regression model where there's no censoring. Here, the Tobit model, the likelihood of that boils down to the likelihood for the linear regression model with normal distributed variables, and that estimator is completely identical to OLS that can also be derived even without assuming anything about the distribution of the error terms, even without assuming anything about the whether there's heterogeneity or not. It may not be efficient, but it's still consistent. This is also what we see. So this is really an illustration that censoring is really costly here. Now we're in a world without any censoring, and everything is fine, even though we assume a log normal distribution, or even if we, add actually quite a lot of heterogeneity. Okay, we still, well, delta, that was, maybe we should not have too many problems at a time. But yeah, you can still estimate if you have a lot of heterogeneity, you can still estimate beta consistently. So that's what's going on. And so I think this illustrates clearly that there are severe consequences of censoring the data or for estimating models with corner solution outcomes. If the underlying behavioral model for the corner solution outcome model or your censored regression model is misspecified, then you're going to get inconsistent results because essentially you don't observe the entire distribution of Y or the underlying latent variable, but you make assumptions about them. If those assumptions are wrong, well, you're going to get wrong answers. Okay, it's like if you put something wrong in, well, you can get something wrong out if you depend on it being right. And in this case, it certainly appears so that is the case. So I'm going to put back this to the staple case, the good old case with normal distributed variables and a little bit of censoring. So let's put that back to that. So we have a natural starting point if we ever come back to this notebook. You can do the second exercises that I did, and I really encourage you to try some out. And, you can also you can try different distributions. I haven't done an exhaustive analysis of this, but here's for example the mix sim distribution looks like this. Well, then you have like two tops here of the distribution, and you're gonna get well, in this case it's not too bad. Maybe we need to increase the standard deviation and now things start to become funny, right? Again, this is because this is definitely not a normal distribution. You can try out different things and look at the consequences for Tobit. I'm gonna put it right back to what we had when we started. So I think really this shows the rise of the machines or the power of the computer, that you can use the computer to simulate and provide intuition of what are the properties of the estimator that you're using. Okay, okay, so let's move on. Now, these assumptions are testable. We can test for homoscedasticity and non-normality. And that's good news, because if you can test for it, well, then you can detect the problems, okay? And you can do something about it. I'm going to talk about that in the next video.